Okay, we are recording and I will share my screen. You can see my screen, right? Okay, so this is the Moodle page for the course. So I'll try to summarize the lectures here. So you need again your IIT Mandi ID to access this Google Sheet, Google Doc. I'll try to summarize it here. I'll also try and provide references. But I'm not sure if I will be able to do it immediately after each lecture, but eventually I hope to keep this up to date. Okay. Okay. Regarding further registrations, already we have crossed around we have come close to 160 registrations. So I'm not sure if I can accept more, but we will see case by case basis. Okay. Okay. So let us continue where we left off. I think we were talking about vector spaces last time, and I just wanted to review some ideas from vector spaces which will be useful to us for the course. But this is in no way a thorough review. These are probably things which you already know. So I'm just touching upon some points here and there. Yeah, so in the last class, we had mentioned about what is a vector. And I said a vector can be anything, right? Provided you give it the appropriate structure, what you want, so that it can be useful to you. So some of the examples of vectors we said were functions, n-tuples, matrices. So these are all examples of vectors. So now using those vectors, we can use the formalism of a vector space, and that will be useful, very useful to us in posing pattern recognition problems. So the informal definition, I would say, of a vector space. So a vector space has comprises of two sets. One is a set V of vectors, and another set F, which is a set of scalars. And this actually is a scalar field. It forms a field. Okay. So field is another type of set which has got certain algebraic properties, and vector is a set of vectors which we are going to deal with. So these two things form the vector space. You can see my writing, right? Whatever I'm writing here. Yeah. Okay. Okay. So so there are certain properties which a vector space must satisfy. And so let's say, for example, you take two vectors, V1 and V2, which are there in this field, which are there in the set of vectors. And we can do various operations. Because we want to be able to perform operations on these vectors. We could, for example, combine the vectors by addition, V1 plus V2. So here by V1 plus V2, we are combining the vectors, and this addition is an addition operation which you have defined on the vectors. And another operation which you can do is take an alpha from F. Let me call it this F. This F is like this. Yeah, and then we can scale a vector alpha V1. So we are scaling the vector scaling this vector with respect to the alpha, which comes from F. So in our case, in most of the situations we will be dealing with, at least for this course, the set F will almost always be R, the set of reals, and the set of vectors, depending on what is it that we will be using. So sometimes, most of the time, it will be a set of n tuples. So the vectors which we will be dealing with mostly are going to be n tuples, and the field which we will be operating with is almost always R. Sometimes it could also be C, set of complex numbers, but mostly we'll be sticking to R. We'll be sticking to R most of the time, the set of reals. So now some of the properties of a vector space is that there is closure. So that means when you combine two vectors, v1 plus v2, the addition operation is closed. v1 plus v2 will give you another element in v. And similarly, this alpha v1 will also give you another element in v. Okay, so basically what it means is that the addition operation and the multiplication operation are both closed in the set f, in the set v. So for example, when you combine two functions, for example, if your set of vectors are functions, when you add two functions, you are going to get another function. You will not get, for example, a matrix when you add two functions. So this is closure. Vector space will also have a zero vector such that 0 plus v1 is going to be v1 plus 0 equal to v1. Special vector called zero vector, and there are some other additional properties. We will not cover everything here, but let's say, for example, associativity, v1 plus v2 plus v3, these are all vectors, is equal to v1 plus v2 plus v3. Okay, so these are associative properties, and this addition property is also commutative. So that means v1 plus v2 is equal to v2 plus v1. v1. Okay, so these are some of the properties of the vector space. We are not going into details. So for example, the simplest vector space which we will be using, or which you are already familiar with, is, let's say, the set R3. You might have heard of R3, right? R3 is nothing but your XYZ, XYZ. So this is your XYZ axis, 3D space. So any point here, let's say I'm calling this V1, is essentially, and so there is your x-axis, this is your y-axis, this is your z-axis. V1 is going to be at a 3-tuple. It has some value x1, y1, z1, which is nothing but the coordinates, the x, y, z coordinates of this point. It's very difficult for me to draw on the tablet, so pardon me. Yeah, I'm not able to draw the third axis. The third axis is somewhere here. Okay, so this is the typical 3D space, the standard 3D space. Let me remove those things. I think that makes it more confusing. Yeah, so that is my vector. And to define a vector space, you have a set of basis functions, or set of bases. So basis is a set which spans the space. Okay, so we will see basis in a minute, but one way to combine vectors is by taking a linear combination, which you might be familiar already. So if you have two vectors, v1 and v2, we can take a linear combination. Let me say, so I can take alpha 1 v1 plus alpha 2 v2, where my alpha 1 alpha 2 comes from f. How did I write f? Okay, this f is alpha 2 comes from f. This f, which I showed before, right? The field, this comes from the field. This. So for example, a linear combination in terms of the space R3 here would be, let's take two vectors from R3, maybe 317. I'm writing them as column vectors now, but in principle it can also be a row vector. So let's say 317 and 210. Let's say these are two vectors. These are my v1 and v2. A linear combination here would be, let's say I take 1.7, 317 plus 2 into 210, which will give me, okay, this, which will give me, what will it give me? 1.7 into 3, I don't know, 2.1. No, 17 threes are, how much is 17 threes? 1 point, this is, let me just write it out. So I can just take, this is 51, 1.7, 0.9, this plus 4, 2, 0. So I'll get some answer, 9.1, 3.7, and 11.9. So this is the linear combination of these two vectors, where I've used the two values, 1.7 and 2, as the alpha 1 and alpha 2. Right? And this, because of the closure property, this is also belonging to R3. And so a basis is a set such that all possible linear combinations will give you each and every element in this particular vector space. So that's called the span. So if you take the set of all linear combinations, it will give you the, that is called the span. And so a basis spans a vector space. So every vector in this space R3, for example, can be represented in terms of linear combinations of its basis vectors. Fine, this is all standard stuff. So, okay, any questions at this point? Any questions at this point? You guys are all familiar with this stuff, I presume. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Okay.
Yes.
Okay. Okay. If you are not familiar, please look up linear algebra textbooks, standard stuff. Some problems we will try to solve on Wednesday. Fine. So now we have vectors. We found linear combinations of vectors. So what after this? What do we do with the vectors? So like that day I was mentioning, you want to be able to characterize vectors and find out more about vectors and their combinations. So one measure which we will be commonly using is the length of a vector. And then we will also, okay, so length of the vector is typically represented by the norm of the vector v1. So so there are so the norm is a very general concept. So you can define your own norm based on what is it that you want to do. But the commonly used norm is the Euclidean norm, or sometimes it's also called the L2 norm. Right? You are familiar, and this is particularly with respect to the n tuples, for example. So, for example, if you have a vector in some Rn, then the norm of this vector. So that means your vector is going to be represented as, your v1 is going to be represented as some, x1, x2 up to xn. Again, I'm just showing it as a column vector. And its norm is going to be the under root of x1 square plus x2 square plus xn square. Right? This is the L2 norm. This is also the Euclidean norm or the L2 norm. One commonly used useful rule is alpha v1, norm of alpha v1 is equal to alpha norm of v1. Okay, where alpha is a scalar from the field. So in general, alpha could be complex also. So in that case, this is just the absolute, this is the magnitude of the absolute value. And if alpha is real, it will just take the positive, the unsigned value of alpha. And this will also give us the idea of a unit vector. So if there is a vector v1, and convert it into a unit vector by, how do you do it? 1 by norm of v1 into v1. So basically you're scaling the vector by its norm. You're scaling the vector by the reciprocal of its norm, basically. And so if your vector is, so this will give you a vector in the same direction, but which has unit length. The norm of this is going to be 1. Let me call this vector as y. The norm of y is going to be 1, right? Because you have normalized the length of the original vector v1. Page after. Another thing which we will use is to represent one vector in terms of another vector. So for that we will usually use what is called the dot product. Again, dot product is with respect to n tuples. And originally the dot product comes from what is known as the inner product. This is a more general definition. If you have other types of vectors, for example, functions, for example, then you can use the more general idea of inner product. But currently we will look at dot product, and you already know how to do the dot product now. So dot product have to be computed. Usually it is computed between vectors in the same space, but it can also be computed in a different way by using projections. Okay. So if you have a dot product v1 and v2, if you have two vectors v1 and v2, and these are n tuples x1, x2, xn, let's say y1, y2, yn. The dot product v1 dot v2 is equal to x1, you know this, x1 y1 plus x2 y2 plus so on, xn yn. Yeah, so this is the dot product. And what will be the dot product? This is going to be an element of f. When you do the dot product, you're going to get something in the field. You no longer have a vector. So basically, if you have through three tuples, and if you combine, if you find out this dot product, you will get a single number. You will get a real number. Then what else? So now a commonly used result. What can you say about the norm of u plus v? Suppose there are u and v are two vectors. What can you say about the norm of u plus v when compared to norm of u and norm of v? What can we say? It's going to be, so if you have two different vectors, what can you say about their sum with respect to their norms? Okay, to make it easier, I will say suppose you take the sum of the norms. Is this equal?
Less than equals to.
Yeah, so this is the triangle inequality, which basically in geometry it is basically saying that the sum of two sides of a triangle is greater than or equal to the third side. Right. So in terms of vectors, this is very general. Like for example, it will work for all vectors for all norms, and to use to actually prove this, you also need another very important inequality, which is the Cauchy-Schwarz inequality. For example, which gives you an upper bound on the dot product, on the magnitude of the dot product. Essentially, what this tells you is that the magnitude of the inner product or the dot product is bounded by the product of the norms. So this is triangle inequality. This is Cauchy-Schwarz. What is this? Cancel. How do I save? How do I save? This is save. Okay. So yeah, and also now we can also measure now distance between two vectors. So the distance d between two vectors u and v is defined as the norm of u minus v. And so now we found distance, and we can also find the angle between the two vectors, which is given by cos theta is equal to u from the dot product by uv. Okay, so that dot product a dot b is equal to ab cos theta. That formula comes from here. So the angle between the two vectors is given by the dot product divided by the product of the norms. And two vectors are orthogonal if angle between them is 90. Implies dot product is 0. Fine. So this is a quick summary of some of the results which we will be using in the next few lectures. So we have a vector space, we have an underlying field, then we have operations on vectors, we have a basis which spans the vector space. So how many, okay, just some general questions. How many bases are there for a given vector space? Can somebody volunteer? How many bases are there? How many sets of basis vectors are there? I'm not talking about the number of elements inside the basis. I'm talking about how many different sets of basis vectors are there. Basis 1, basis 2, basis 3. How many are there? Yeah, there are infinite number of basis vectors. There are infinite number because any linear combination or any scalar multiple of a basis set gives you another basis set. Infinite number of basis vectors are there. So now we defined the idea of vectors. So although most of our discussion was with respect to vectors of the form of n tuples, in principle, all of these ideas are applicable to any type of vector. So the vectors could be functions, the vectors could be matrices. Fine. So you can linearly combine those vectors and get another vector. And yes, so now, so we have a vector space which has vectors. We found out methods to combine the vectors. linear combinations are the simplest, so we will stick to that. Then we found out about, once you have a vector, you want to find out some things about the vector. You want to find, for example, its length. So for that, you can use the norm. Then, so this is the standard L2 norm or the Euclidean norm, which we will be using, but there could be, based on the applications you are trying to use, there could be other types of norms. Can somebody give me an example of some other norm for Rn? Supremum norm, okay. Supremum norm, she has said that. Supremum is, I think, mostly for continuous spaces. So in some sense, it is like the max, okay. Any other norm? You must have heard of L1 norm. Yeah, L1 norm is basically just the sum of the elements, and also the L0 norm, which is the number of non-zero elements. So based on the different applications, we'll be using different norms. Then we saw about unit vectors. So if you divide a vector by its norm, you will get the unit vector in that particular direction. So essentially here in this, again, sticking to 2D space, what I meant by unit vector. So this is the space R2. So I have x1 here, let's say, and this is x2 here. So can you tell me a basis for this space, R2 space, x1 and x2? Standard basis. What is the standard basis? 1001 is the standard basis for the space. Right? 1001. Yeah. What about 3217? What about this? Is this also a basis for the space? Yes.
Yes.
3217 is also a basis for the space, primarily because these two vectors are linearly independent. Right. So that is one of the conditions of the components of a basis, and they also span the space. 3217 also spans this particular space. So that means any point in xy or in this R2 can be represented as a linear combination of 32 and 17. So it forms a basis. Similarly, 1001 is the standard basis. Any element, any vector in R2 can be represented as a linear combination of 1001. Whereas 3264 is not a basis because these two elements are linearly dependent. These two elements of this set are linearly dependent. Yeah. Okay, so you guys know all this. So yeah, so you're talking about unit vector. So suppose I have a vector here. Some vector is there here. Okay, this vector is here. This is this vector. So in terms of the standard basis, let me call it x1 and this is x2. So in terms of standard basis, this particular point is basically x1 of 10 plus x2 of 01. This is this particular vector, and it has got some length. So now when you divide it by its unit norm, it is essentially going to give you a vector like this in the same direction, but the length of this vector is going to be 1. That's basically what it means. Yeah. Anyway, I think if you are not familiar with these things, you will the problem solving session on Wednesday will help you. yeah, we also talked about dot product. So dot product is if you want to represent one vector in terms of another vector. So then you can use the dot product. So you can take the dot product between those two, and that will kind of give you an idea of the similarity between those two vectors. So in general, the higher the dot product magnitude, the more similar they are. Okay, so you can just think of it vaguely, I mean loosely now in that way. And these are the Cauchy-Schwarz inequality and the triangle inequality are useful results which will help us in maybe proving some results or anything like that. But these are like standard results for all vector spaces. So now we have then to find the distance between two vectors, we find out the difference and take the norm of that. And cos theta, I mean the angle between two vectors can be found out by taking the dot product and normalizing it by the product of the two norms. And we also found out what is orthogonal. So we have summarized this. So basically now we have vector spaces, we have vectors, we have a way of we have several ways to operate on those vectors. We can combine them, we can compare them, we can find out the angle between them, you can find out the distance, you can find out the size or the length. Right? So these are all operations which we will use. Now, how is all this useful to us in pattern recognition? How is it useful to us in pattern recognition? It's useful to us because we are going to deal with features. For any pattern recognition system, we are going to deal with features. Where is it? Yeah. We are going to use features. And in many cases, our features will be some n tuple in some r raised to n. And so all these formalisms will be very useful to us. We will be able to, once you represent your data as features in some vector space, you can use all of these tools to infer more about those, about the data. So you'll be working with the feature space. So these features could be a simple handcrafted feature, or it could come from a convolutional neural network, or it could be, I mean, so it can be any sophisticated feature also. But once you reach this representation, then it is a question of how you compare vectors. And that is what is going to help us. Okay, another thing which will be useful to us is matrices. So I already said a matrix can be a vector, but in this particular situation, what I'm telling you now is we are not going to view matrices right now as vectors. If needed, we can use them at some point, but right now our objective of using matrices is as linear transforms. So what is the linear transform? A linear transformation or a mapping or a linear map is a transformation from one vector space, let's say I call this V, into another vector space. And you can use a metric, let's say A, which will transform a vector in this space to another vector in a different space. So this is mostly how we will be using a matrix. Right? For example, if I have a matrix A, which is of size m by n. If we are currently talking about only real matrices, real valued matrices. And it's of size m by n, and then we take this matrix vector product Ax equal to B. Essentially what is happening is, so basically A is m by n, so x is going to be n by 1 and B will thus be m by 1. So essentially this matrix A has transformed something in r raised to n to r raised to m. So we have r x here is a vector which is n cross 1, which is basically a vector in r raised to n, and b is a vector in r raised to m. So this transformation has basically transformed my x from vector space Rn to another vector space Rm. Right. So this is the mapping which it is doing. So for example, consider A as this matrix 3 1 1 3, and let me take my x as 2 1. Okay, this is my x. So what will this give me? 3 2 are 6 plus 1 7, and 2 plus 3, which is 5. Oh, sorry. In this case, our matrix had to, this was a square matrix, so that is why it is still in the same space. But we can have, let's make it another vector. I didn't think of this. We take another. Three, 1, 1, 3, 1, 2, let's say. Okay, so this is now 1, 0, let's say. One, 0, 2. What will this give me? 3, 1 are 3, 1 into 0 is 0. So this will give me 5. 1 into 1 is 1, 0 plus 4, 5. Okay, so essentially my element, which is my x, in R3 has become B, which is in R2. Okay, so suppose you do this transformation. So this was just an example. So this transformation, this is basically a 2 by 3 matrix, right? So this is from R3 to R2. So for example, you must have heard of principal component analysis, PCA, right? So PCA is commonly used to reduce the dimension. Or there are other techniques also to reduce the dimension. Now, for example, a 3-dimensional vector here, you might want to change to a 2-dimensional vector in such a way that the most of the representation or most of the information contained here is preserved. So this matrix, of course, is not doing that, but still this gives you an idea of how to use matrices as linear transforms. Essentially, the matrix which represents the PCA is essentially basically a transformation from one space to another space. So another useful result, again in the same topic, when we restrict ourselves to square matrices, is transformations of the form AX equal to lambda x. In this case, so A is square, A is a square matrix. So in this case, what is happening here? The linear transformation which you do here, the transformation done by this matrix, is equivalent to a scaling. And x form the set of eigenvectors for this matrix, and lambda is a corresponding eigenvalue. Right. So I think this was my example which I wanted to use. Let's take 3 1 1 3. This was the matrix. So 1, 1, for example, is an eigenvector for this matrix because this will give me 3 1s are 3, this will give me 4, this will give me 1 plus 3, 4, 4, 4, which is essentially 4 into 1, 1. So this is my lambda and this is my x. Yeah, so 1, 1 is an eigenvector for this particular matrix A. What about 2, 1? So 3, 1, 1, 3. Let's take the matrix 2, 1. This will give me 3 2s are 6 plus 1 7. 1 2s are 2 plus 3 5. So now you can see that 7 5 is not a scalar multiple of 2 1. Right? 7 5 is not a scalar multiple of 2 1. So hence is not an eigenvector. So what does it mean geometrically? So geometrically, let me just quickly draw it here. So for example, when in the first case, when you take this case, for example, 1 1. So let me, this is, okay, this is, let's say 1 and this is also 1. So I have this vector 1 1, which is essentially this. Okay, this is 1 1. And when you transform this 1 1 using A, you are getting 4 4, which is again a scalar multiple, right? Oh, sorry, 1 2 3 4. Luckily, 4 4. So the direction, the vector points in the same direction. It might flip. That's a different matter. If the lambda is a negative one, it might just flip. But the direction, the orientation of the vector does not change. But whereas if you take 2 1, for example, let me take this. Whereas 2 1, 2 here and 1. This is my vector 2 1. If I take 2 1, the answer I'm getting is 7 5, which is, let's say, approximately 4 5 6 7. So 7 5 is maybe somewhere here. So now this red vector basically becomes something like this. Yeah, it's not exact, something like this. So essentially what has happened is, in this transformation, this matrix rotates and scales the red vector because it is not an eigenvector. Whereas if it is an eigenvector, there is no rotation, it will only scale. Right? So that is the geometric meaning. So eigenvectors, I mean, we are talking about square matrices. So for square matrices, eigenvectors of the square matrix, when you apply it as a linear transform, have only scaling. Whereas non-eigenvectors will have usually a rotation and a scaling. Okay, I will stop here. This is the only linear algebra which we will cover. And if there is anything more, we will be covering it as and when needed. Okay, so I'm assuming that you will be familiar with these operations and what we have done. So you can review the appendix in Duda Hart's book. You take the appendix. It contains a lot of things. Linear algebra is also covered in that. You can have a look at that. Although this material I've taken from various places here and there, but this is only a summary. What I've given you is just a summary. Right. Any questions at this point? Okay, if there are no questions, we can stop here. I will share the recording also online, and we can meet tomorrow. Maybe we'll meet online only. I'm not sure. If unless you get a mail from Dean Infra or somebody, Dean Academics. Okay, so assume that right now that the tomorrow's lecture is also online. If it is not the case, I will send you an email. Okay, then. Thank you. We'll meet tomorrow. I'm stopping the sharing.